Early geologic history of the northwestern United States was characterized by a short-lived but intense magmatic episode from 55 million years to 40 million years ago. The episode resulted in an extensive and computationally diverse belt of volcanic and plutonic rocks extending from the southern British Columbia across northwestern Washington, central Idaho, and into Montana and Wyoming. Although the time equivalence of this belt of geologic rocks has been recognized and some basic geologic, geochemical, and radiometric work has been completed, the magmatic event remains poorly understood within the context of tectonics of the Northwest. The Challis Volcanic Field of central Idaho is the largest and most diverse of the Eocene volcanic fields, both in composition and in variety of volcanic deposits. Because it is dissected to subvolcanic levels, geologists can study the geochemical relationships among cognetic, volcanic, and intrusive units and internal structures of the volcanic and hyperbolpass complexes.
The Challis Volcanic Field is a part of an extensive Eocene volcanic belt in the Pacific Northwest between 42 and 49 degrees north latitude. The belt extends 1,500 kilometers from west to east and includes the British Columbian Alkalic Province, the Sampoil Field in northwestern Washington and southern British Columbia, the Challis Fields in central Idaho, the Absaroka Field in Montana and Wyoming, the Montana Alkalic Province, and numerous small, scattered outliers of Eocene volcanic rocks. The Eocene volcanic belt was originally named the Challis Arc, which was held led to an acceptance of the volcanics as being subduction related. However, recent work suggests that this tectonic interpretation is too simplistic. We therefore propose that the name Challis Arc be abandoned for the Eocenic volcanic deposits, because the term arc implies a subduction related origin and such a tectonic setting remains to be demonstrated for these igneous rocks.
The Challis Volcanic Group of central Idaho is exposed over an area of about 25,000 square kilometers and forms the largest subregion of Eocene volcanic rocks in the northwestern United States. The rocks were deposited on an irregular pre-volcanic terrain underlain by Precambrian crystalline rocks and belt supergroup, Paleozoic sedimentary rocks, and Mesozoic Idaho batholith. Stratigraphic relations in the Challis Volcanic Group are complex as a result of deposition on that irregular surface. The most voluminous volcanism and plutonism occurred in the interval from 51 to 45 million years ago, with minor silicitic intrusive activity persisting until 40 million years ago. Volcanism involved the construction of composite cone complexes during effusion of intermediate lavas and the formation of calderas associated with explosive ash flow eruptions. Intrusive rocks were emplaced as plugs, domes, dike swarms, and composite stocks. Volcanic deposits of the northern Challis Field can be subdivided into several stratigraphic packages. These are, from oldest to youngest: 1. Intermediate rocks, dominantly andesite lava flows; 2. Rhyodacite to rhyolite ash flow tuffs; and 3. Rhyodacite to rhyolite domes and plugs. Volcanism began about 51 million years ago with the effusion of voluminous intermediate to mafic lava flows. The early intermediate to mafic lavas are largely covered by ash flow tuffs on the northern and western parts of the field, and the early intermediate rocks are therefore best exposed in the southeastern part of the Challis Quadrangle. Early effusive volcanism was followed by a period of explosive rhyodacite to rhyolite volcanism, resulting in subsidence of the Van Horn Peak Cauldron Complex, the Thunder Mountain Caldera, and the Twin Peaks Caldera during the brief interval of about 49 to 45 million years ago. Waning stages of igneous activity in the northern part of the Challis Volcanic Field were characterized by the emplacement of rhyolite to alkali rhyolite domes and intrusion of the granite Castro-Pluton in the lower part of the ash flow tuff sequence. Dome emplacement was controlled by cauldron ring faults and by extensional structures.
Mineralization within the Challis volcanic group is associated with volcanic and plutonic activity, such as the emplacement of the domes and plutons, caldera collapse, and world-spread hydrothermal activity. Regional structures such as faults, fractures, domes, and grabens controlled the location for vein-filling precious metals and hydrothermal activity. The most profitable minerals mined from the Challis volcanic field include gold, silver, copper, lead, zinc, and building stone. Also in place due to Challis igneous activity were beryllium, thorium, tin, mercury. The map below shows locations of productive gold and silver deposits which have been mined along the Trans-Challis Fault Zone.